Hello and welcome. In today's video, we're going to talk about the length of a curve. You will remember that we introduced parameterized curves as a mapping that maps some interval of time to points in R to the n. So the trace or the graph of that mapping is then the curve in n-dimensional space. We would like to know how long such a curve is, and in this video we're going to find a method for computing that. So the goal today is to compute the length of a curve. We're going to make one assumption that will make our lives a little easier. We're going to assume that the derivative of a curve gamma is nowhere zero in the interval that we're interested in. The reason for that is if the interval is zero, then the movement might turn around. So you might get a curve that moves in that direction first, then slows down, and then turns around. So after moving in this direction here, we might then be able to turn around and move in the opposite direction, back this way. And it's not really that meaningful to assign a length to that curve because we go through that curve twice. But actually we're back at the origin, at the point where we start with when we go through the curve backwards a second time. So to make things a little easier, we're going to assume that the derivative is not zero anywhere, so we can't have these turnaround points. It doesn't make that much of a difference, however. So if you encounter situations where this actually happens and you still want the length of the curve, then either you compute the length up to that point, or you just split at that point if you want backward and forward motion together. Okay, so in the following, we'll assume that for a curve gamma, the derivative is nowhere zero. So gamma is defined on an interval, maps to R to the n. We will assume gamma dot of t is not zero for all t in I. And this is an assumption we make in this video only for the moment. Okay, the basic idea is then to approximate the curve through a polygonal path and then compute the length of that polygonal path and subsequently refine that polygonal path by making the polygons shorter and shorter until we get closer and closer to that curve. So we want to approximate the curve through a polygonal path. Now it looks like this. Let's say we have a curve like this here, and we're going to approximate it through a polygon. And of course we need start and end points, and we'll just designate some points in between, like here, 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 and say one more here. And then we'll look at the polygon that just connects these points. All of these orange lines are straight, so we can compute the length of that polygonal path easily. And we call these points, or the times that correspond to the points on this curve, we call those t0, T1, T2, and so on. in this case up to t5. Okay, so we have an interval where gamma is defined on. So let gamma be defined on an interval alpha beta to r to the n. And then we choose points in that interval. The first one is the same as alpha, the start of the interval. Then we choose a number of points in between. And the final point is Tn, that is equal to the endpoint of the interval beta. And then we can compute the length of the polygonal path associated to that. So that polygonal path then passes through the points gamma of t0, gamma of t1, and so on, up to gamma of tn. That length, we'll denote that by ln for now, is then, well, it's the sum of all the partial paths here. And each part of that polygonal path has a length of gamma of tk minus gamma of tk minus 1, and then we'll just take the norm of that. Okay, so this is the length of the polygonal path. And just as a quick side note, this is always less or equal to the actual length of gamma because of the triangle inequality. So we've taken shortcuts with this polygonal path. And we'll denote this length of gamma as S of gamma from now on. So how does that help us with the computation? Well, we need a brief reformulation to see where this is going to lead. What we want is, we want to somehow reformulate that as an integral. So we will need to represent the summons of this sum as something of a form function value times length of an interval. Yeah, because we want this to be a Riemannian sum, and then in the limit it's going to be an integral. So the length of these intervals clearly is tk minus tk minus 1. Tk is always bigger than tk minus 1, so we don't need an absolute value here. So this is the length of an interval for two subsequent points. And if we want to reformulate it like this, well, we just have to put this gamma of tk minus gamma of tk minus 1 here that we actually want. Divide that by tk minus tk minus 1. So that factor cancels out. And that factor here, this tk minus tk minus 1, that's a real number actually, a positive real number. So we can just write the norm around this whole expression without changing anything. Okay, so that's precisely the same thing as this expression here, just written in a more complicated way. What we have gained by that is this here. This is now the length of an interval. It's the length of the interval tk minus 1 to tk. And this here could be interpreted as the value of a function over this interval. For some point in the interval. And now let's make the intervals smaller. Let's choose more and more points and make the interval smaller and smaller. What happens? Then, well, this sum is going to converge to an integral over this function expression. And this function expression here that's the interesting point, this function expression, that is converging to the norm of, well, that the quotient in here. If we move tk and tk minus 1 closer and closer together, so we're taking the limit, then this becomes the derivative of gamma. So this is moving towards the derivative of gamma. So what you can see here is that whole thing here. If we take more and more points and also reduce the interval length at the same time, then this whole thing converges to the integral of the norm of gamma dot of t dt. Because it's a Riemannian sum and we refine that sum more and more. Okay? For interval length, so the maximum interval length over all k, tk minus 1 to 0. So we need to choose the points in a way such that the interval length actually goes to 0. And then this convergence to the integral will happen. That's precisely how you can compute the length of a parameterized curve. The actual proof is a little more involved, but that is the basic idea here. Of course, you have to work out some technicalities, but I'm going to spare you of that. So let's just write down our result here. For a parameterized curve, we can compute the length of the curve as the integral over the norm of the derivative of the curve. So let gamma, defined on an interval from alpha to beta to r to the n, be a parameterized curve. And remember, that means it's at least piecewise differentiable, piecewise continuously differentiable. And we assume that gamma dot of t is nowhere 0 for all t in alpha beta. Then the length, and that length is usually denoted by s of gamma of the graph of gamma, that is also referred to as the length of gamma itself. And that length is given by s of gamma is equal to the integral from alpha to beta over the norm of gamma dot of t dt. Let's see a quick example to see how this is actually computed. We're going to look at the logarithmic spiral. Remember, that is defined as the curve gamma on the interval from 0 to infinity, mapping to R2. And the function is defined as gamma of t equals e to the minus t cosine t sine of t. Remember how that looks like. So we have a coordinate system here. then for t equals 0, the point that we get is the point 1, 0. So we start here at 1, 0. And then we make a motion in a circular motion. At the same time, we decrease the radius more and more, circling into 0. So what happens is we get a spiral that's moving inward somewhat like this. That's called the logarithmic spiral. Okay, so we want to compute the curve length of this spiral here. To do that, we first need to determine the derivative of gamma. Gamma prime, gamma dot. That is minus e to the minus t cosine t minus e to the minus t sine t. For the first row. For the second row, we get minus e to the minus t sine t plus e to the minus t cosine t. I'm using product rule here to compute that derivative. So we can factor out the e to the minus t, makes it a little nicer to look at. And then we have minus cosine of t minus sine of t. And here we get minus sine of t plus cosine of t. Now that's the derivative. What we need is actually the norm of that derivative. So that is the square root of, let's see, we have e to the minus t squared. That's a common factor. And then we have this minus cosine t minus sine t squared. Plus, that second factor here, minus sine t plus cosine t squared. I'm going to turn this around. I'm going to write that as cosine t minus sine t squared. Okay, we can take this e to the minus t squared out of the square root. So that's just e to the minus t. That's a positive number anyway. And then for the terms inside of the square root, what we get here is, well, minus cosine t minus sine t squared. We can take out the minus squared here. So that's the same thing as cosine t plus sine t squared. And this, on the other hand, is the same thing as cosine squared t plus 2 cosine t sine t plus sine squared t. And then we have this second expression, cosine t minus sine t. That is the same as cosine squared t minus 2 cosine t sine t plus sine squared t. Okay, you can easily see some factors cancel out here. Specifically, what we get is we have a plus 2 cosine t sine t here and a minus 2 cosine t sine t here. So those two factors cancel out. And then we're left with 2 cosine squared and 2 sine squared. So all in all, that is the square root of 2 cosine squared t plus sine squared t. Now cosine squared plus sine squared is 1. So what we get is e to the minus t square root of 2. And now finally, to get the length of that curve, S of gamma, we'll have to compute the integral over gamma dot of t, norm dt, in the interval, so from 0 to plus infinity. And that's the integral from 0 to plus infinity over e to the minus t square root of 2 dt. We can just take out that factor square root of 2. and then we integrate e to the minus t. That is minus e to the minus t from 0 to infinity. So what we get here is, well, upper bound e to the minus infinity, that's 0 or minus 0. And then we have minus e to the minus 0, so it's plus e to the minus 0, that's 1. So what we get in the end is a length of square root of 2. So that's the length of that curve, and that is a somewhat surprising result, I think. The curve is infinitely, because the time runs up to infinity, and still it has a finite length. One thing I like to mention is the length of a curve should, of course, always be non-negative. So if you get a negative number here on an exam question, you most probably messed up somewhere. That cannot be the right answer. Okay, so pay attention if this is on the exam. Okay, so that's it for the length of curves. In one of the following videos, we're going to apply this to define an integral over a curve in a similar way. I'll see you then.